Hi guys, as promised, this is the discussion concerning lab 5. Some of you asked during the class, and at that time we were at the end of long session after 2 or 3 hours or something. So I'm going to share with you here basically the solution to the dilemma. Okay, so I'm sharing with you here the screen. So this is from the vantage point of the station being stationary, and the spaceship is moving with a velocity beta c, basically. Remember, beta is given to be 3/5, so the velocity in this case is 3/5 the speed of light. And in the lab, it gives you instructions on how to do the conversions so that the units of the time are actually in microseconds, and the speeds are in terms of beta, and all of the things, and the distances are in meters. So there is instructions. Hopefully you guys have worked that out. Anyway, the event when the front of the station, first of all, the front of the ship, I should say, because it's the ship that is moving now, whose length is supposed to be 400 meters, but from the vantage point of the observer, it's 320 meters only, because it's moving with a velocity beta in this case, so its length contracted, and beta happened to be 3/5, so if you plug in the numbers in here, it's going to be 4/5, the square root of this whole thing. 4/5 of 400 is 320 meters. Anyway, then the back is governed by the same equation as the front, except it's at 320 meters away. Okay, so this is the equation for the back, and this is the equation for the front. So when the front passes by the front, that means x is equal to 0. Remember, we are taking the front of the station to be the origin. So at that point, all I have to do is equate that to 0, and from here I can find so this will happen at t equal to 0. So at t equal to 0, the spaceship starts entering the station. Okay. When the front has reached the back, the front has reached the back. Okay. So the equation for the front is beta ct, but the station is 350 meters. So when I plug in the numbers, I find that it happened after 1.94 microseconds. So this is now the front of the moving spaceship getting into the back of the station after 1.94 microseconds, if I did the algebra correctly in here, and then the back passing by the front. So remember, the space station in here has a front and has a back. So when the back passes by the front, that means x is equal to 0, and this is the equation of the back for the ship. So all I have to do is plug in this equation and equate it to 0. So that is when the coordinates of the back are equal to 0. That means now the back has just crossed into the to the station. If I solve for the equation here, I find this happens after 1.78 microseconds from the time when this whole thing starts, from the time when this thing starts. So which means that for a whole 0.16 microseconds, the entire ship is inside the station. So it fits. Okay, so there is no mystery in here. It fits perfectly inside of it, so there is no problem in here. Okay. And if you guys have any difficulty with this math, this is the delta t that you're supposed to report. Okay. Now, here is where the simultaneity is. For me, sitting in the station, I see both ends of the station as a simultaneous event. So the measurements of the 350 meters that I measured is actually in the same time. So that's where the simultaneity is. Now, from the spaceship vantage point, if you are sitting on the spaceship, you see in this case the station rushing to you with a velocity beta c in the opposite direction, of course. So you use a transformation, Lorentz transformation, and you go about it. Okay, these coordinates are measured in the rest frame. These are what measured in the station itself. So the x is in the station, the t is in the station. The x prime and the t prime now in this moving frame as we're sitting in it. Okay, so for the front, remember what we're trying to measure now is not the coordinates of the spaceship. We're measuring the front of the station as it's moving toward us. So the front of the station now is moving with this velocity. So all I have to do is take Lorentz transformation, gamma times x minus beta ct, and put x equal to 0. Okay, so this is the equation for the front of the spaceship. but in terms of the time and not in the time of my frame, not the time of the spaceship, in terms of the time of the station. The time also in the station and the time in the spaceship are governed also by the same Lorentz transformations. So in this case, T prime is equal to gamma times T. The coordinate of the front is 0. So in this case, it's going to be gamma T. T, just get rid of this T common T. Actually, gamma times T is equal to T prime. So it's going to be minus beta times C times T prime. So this is the equation of the front of the station moving toward us. Okay, so this is the front. In the same fashion, for the back of the station is 350. Remember, these are the coordinates in the station reference frame. So you cannot use length contraction because this is the coordinates as reported to me from that reference frame. Okay, so in that frame that thinks it's rest, we know it's moving. We know the station is the one that is moving from our vantage point. Okay, so in this case, it's 350. That's the back. Plug into this equation, so it's going to be gamma times 350. It's the same Lorentz transformation, except now I have 350 instead of putting 0 for the front of the station. I'm putting 350, and T prime is this one. So it's a matter of getting rid of this T in favor of T prime so that I can report things in my own coordinate prime system for the station. So I can tell you where is its front and where is its back all the time. So I'm going to use the same thing in here. So I solve for T, this equation, and plug it back into this equation. So it's going to give me X prime as a function of T prime. Now get rid of this because I will have a gamma factor in here, and I have 350 times 1 minus beta squared, which is actually 1 over gamma squared. So after I do the simplification, I will end up with 350 over gamma. And that is your length contraction, if you wish, for the station. In other words, the station has shrunk by a factor of gamma 2. To now its length is not actually equal to 350, but rather is 280. Okay, so again, we solve for that equation. We solve when would the back of the station crosses the front of the ship. So this is the equation for the this is the equation for the back of the station as it's moving in time, in our registered time, with our marking of the coordinates, and in the front of the ship now, this whole thing is equated to 0. And this gives me a solution for a time of 1.56 microseconds. So of course, the front now is moving, of the station is moving to the front. And so we have that solution, we have that time. This is the back and the back. We really don't care about this one, okay? This means that the ship has crashed actually into the back. We don't care about that value in here. I mean, but you're supposed to report it anyway. And you're supposed to do the other one, the back and the back in here too. I didn't do it because it's an irrelevant question, honestly, for this particular dilemma. It's the back of, when would the front of the station reach the back of the ship, basically. And that will happen if I solve this equation and put it equal to negative 400. Because now I am in a ship that has length of 400. My original coordinates is at 0, and the back of my ship is at negative 400. So the equation of the front of the station is given by this expression, minus beta CT, where beta C is equal to 180 in those units. So it's minus 180 T prime now is equal to negative 400, the whole length of the ship. So in this case, if I do the calculations, it happens at 2.2 microseconds. So there is a time, actually, a good time, for the entire ship also to be inside the station. Again, you do the calculations in here. You equate this one to 0. That means the back of the station has just crossed the front of the ship. So this is when the front of the ship, if you wish, in this reference frame is inside the station. A moment later, the back of the ship will also pass through. Okay, so in this case, that means that for this whole amount, which is this difference between this amount, 2.2 microseconds and 1.56 microseconds, for this whole time, the ship was actually inside that station. Okay, and again, when you graph them, the first graphs are the slopes are positive, and this is 350. This is the length of the station, and if you do the equations in here, this is when the front of the ship crosses the front of the station. This is when the front of the ship crosses the back of the station. This is where the back. This is the equation for the back. This is where the back of the station crosses the front of the ship. As long as this event happens before this one, which is the case, then you're in good shape. That means that this is good, and that's true. This is for the first case. That is true. Okay, the first event is actually this one, when the back goes by the front, and then when the front gets to the back, which is fine. And that's exactly what's going on. So this event happened first, and then later this event. So in other words, the back crosses before the front actually smashes into the back. So in this case, it fits, at least for this length of time, 116 microseconds. Here, and this scenario is the other way around. The slopes are negative, by the way. In this case, they're minus 180 T primes. And the ship, the length is 400 meters. So this is, if this is 0, this is negative 400 meters, okay? So now what we're concerned with is this event first happening, meaning that the front of the station, which is this point, crosses, I'm sorry, the back of the station first in here, and this is, sometimes it's confusing. You really have to think through what you're saying, otherwise you get confusing. So again, this equation in here is for the back of the ship, okay, in this frame in here. And the back of the station in this frame in here. So when you equate it to 0, you are at this event. So this happened at 1.5 microseconds, and then when the back of the ship is actually crosses the front of the station. So this is the value in here. And at the end, the station, I mean, the ship is for this long time, it's inside the station. So both of them are resolved. How do you resolve it? The question was about question 4. The question 4 has to do with simultaneity, okay? What was simultaneous in the first event, which was the length of the entire ship, the entire station, now is not. Simultaneity is actually the length of the ship itself. Those are simultaneous event from the vantage point of the person sitting in the ship. And the other two events are no longer in the same event. Namely, the front and the back of the station are not in the same time. So this is the answer to question 4. Okay, go do the math again. Go through the algebra and be meticulous with it. If you have any questions, please let me know. But this is the answer to this problem in here. Thank you.